in a tick. Cool. Hey everybody, and welcome back to week 12 of Fastbook Reading Group. So I think looking back, it's actually almost 3 months, and it's so great to see that we've been at this for 3 months now, or 12 weeks. It's almost 3 months, but 12 weeks, and we've been doing this week after week, and we've been coming back. So I thought before maybe getting started today, it might just as well be helpful to just have a look at what all we've covered. So if I go to Fastbook, this is the repository, and you already know we have the playlist. If I go weights and biases here, I go to the weights and biases channel, and you can see the videos. So we already have the playlist. If I go to that playlist, which is this one. So we've got everything in a playlist here, and I thought it might just as well be helpful to see like how much ground we've covered. So we kind of, I was just going through, because I was drafting a tweet today just about Fastbook, and I was having a look at like what all what's all the things that we've done, and having a look at just starting from our journey. And I remember with Jeremy, before we started intro and before we started even the first chapter, I remember making a call, and I remember as a group we decided that we're going to stick to this and we're going to end Fastbook together. And we've covered really quite a bit. Like we started with this was the chapter where we learned how to put things in production for the first time. We skipped over ethics for over time, but we looked at MNIST basics, where we learned how to classify, basically digits or handwritten digits. And in pet breeds is where things started getting a little more interesting, where we started doing a bit of an actual problem that's a more real world related problem. And in so this was all classification, and we were just starting up basics with classification. And then when we got to multicat, the next thing we started looking at in multicat was how we can do multi-category classifications when an image has multiple labels. So what to do with that. And we saw that FastAI kind of it's really easy to solve. It's really easy to work with FastAI, and like with multicat, there's not a lot that needs to change. All we had to do was just let FastAI know that we're working on this multicat problem. And we looked at the loss functions, how the loss functions changed, and we found this idea of like using sigmoid instead of softmax. So those were the main changes when we got to multicat. And in sizing and TDA, we actually started looking at the data augmentations. We started looking at what test time augmentation stands for. And finally, we got to collab. And when we got to collab, this was about movie recommendation systems. So we learned about, basically we learned about movie embeddings, or we learned about user embeddings, and we learned how these various recommendation models are built. So it's the concepts that we learned were not just for movie recommendation, but these were concepts that could be used in product matching, or in basically getting a good understanding of the customer user base. And now I'm so excited that we add this chapter convolutions. So we skipped over tabular and we skipped over NLP. As I've mentioned, tabular is something that Zach Miller is going to come, and he's going to touch on tabular. And for NLP, it's still in the works, but I will share plans about what we have for NLP. So that's something that will come in a few weeks. So what we're going to do now is we're going to look at convolutions today. And convolutions will form the basics of basically every convolutional neural network has convolutions in it, right? So what we're going to cover today is going to look at what convolutions are really, as in what does a 1D convolution mean? What does it mean when we say 2D convolution? What does it mean when we say 3D convolution? Or like, what's the exact mathematics, or what's the exact operations that are going every time that we say, oh, we're doing a convolution operation? And then that will form the basics for like ResNet. And something I do want to highlight right now is that, so let me go to the forums. And something I do want to highlight, so as I mentioned, we've got the forums. And if you go to this paper reading group forums, let me paste that link in the chat as well. I'm just pasting that link. So there it is. So one thing that you will see is happening on the side is that we're starting with paper reading groups where we're starting with beginner friendly paper reading groups. So we're starting with ResNet, DenseNet, Squeeze and Excitation, and then Efficient Nets. So those are going to be very beginner friendly paper reading groups that we're going to start looking at. And you see that Fastbook also has ResNet in it. So I think this would be a really good point if you really want to start. The reason why we're doing this is so people from Fastbook can transition easily into paper reading groups. And like it does require a good sense of like being able to read the papers and being able to understand the papers to be a really good deep learning practitioner. So what we want to do at Weights and Biases is as I mentioned right in the first week, is that we want to support you become good deep learning practitioners. And this is going to be the point that could be a transition point where we learn the basics about convolutions and then we go to ResNets and we could shift to having weekly paper reading groups or bi-weekly paper reading groups. So then after that point, the platform for vision would be set, and then you can go back to like having more cattle competitions or participating in more cattle competitions. So that's how kind of my journey started as well. And I'm trying to just mimic that for what worked for everything that worked for me, and I'm just trying to mimic that for this group, and it's worked so far. So that's this idea that I did want to share about beginner-friendly paper reading groups. And if I go to the Fastbook reading group and I get to week 12 discussion thread, so as is usual, if you go to 1db.me Fastbook 12, which is the link that I'm going to paste that in the chat as well. So this is the link where we're going to have all our discussions today. So if I go to 1db.me/fastbook12, oh, I think I sent the chat to Angelica, but she's shared it. So if you get to 1db.me/fastbook12, this will bring us to this discussion thread, and this is where we're going to have all our discussions today. I usually highlight the blog posts and through PowerPoint presentations. I thought maybe let's try something differently. Angelica has this really nice, Angelica curated this really nice list, and I'm so glad to see that many of you are still coming back, like even week 12, and you're still writing these wonderful, wonderful blog posts, which is really great. So Vinayak wrote about this anime recommender system with FastAI2, and Ravi Mishru then wrote 2 blog posts about part 1 and part 2 about building a movie recommender. So he's got this Netflix, which is just everything that we covered in our last sessions about Movie Lens. And then there's this other one, which is part 2, that does a recap and goes more into the detail of like what exactly are user embeddings and like what are biases and everything that we covered. And we've also got the blog post from Ravi Chandra, which is about, again, he's been coming back week after week. So you can see how this Fastbook has lots of these wonderful different blog posts. So that's the resources. And then one thing I was really excited to see as well in the forums was, in terms of projects and resources, I saw there's this create a movie recommender which is a discussion started by Ravi Mishru. So I was really excited to see this discussion. And in this one, Ravi's mentioned that he's been working on building, like he's written this blog post about movie recommender systems. And the idea is to then use what we learned in chapter 2. So remember in chapter 2, we learned how to put things in production, and we built like a system that could classify basically images, and it could predict what the image labels are. Ravi wants to do that for movie recommender systems. So he wants to build basically an API and deploy it in the cloud. So I think this is a really, really interesting project. And if you want to be involved, please come and join this thread. So let me just post that in the chat as well. Okay, so with that being said and the background provided, I think we are now ready to get started with convolutions. So as part of convolutions, as I've already mentioned, what we're going to do is we're going to look at what the exact operations are for convolutions. So I kind of touched upon how convolutions are things that can be used to like detect edges, or they can be used to they can be used to detect horizontal edges, or they can be used to detect vertical edges, or they can be, there's like these convolution filters that can blur an image, or it can sharpen an image. And there's like all of these different things that convolution filters can do. What I didn't touch upon is like how that magic happens. So it's my so today I'm going to actually start doing that. So one thing, when we were looking at convolutions last time, we saw that if you have an image like this, and remember, if this is 3, right? So let me just go back to that image that we have here. So see how this is just a snapshot of that digit 3. So in this one, you'll see like everywhere where the number is 3, like these edges, every point in this image, that has a darker pixel value. So all pixel values, if it's a bit image, all pixel values are between 0 and 255. And as we can see in this pandas data frame, so in this case, the 255 represents black. It could be that in different places this could mean different things, but for our sake, when we're trying to look at this chapter, let's just say 255 represents black. So all of these pixels that are the digit 3 themselves, they're going to be high values. So these are going to be of values of around 200 to 255 range, right? And then everywhere around surrounding, that's just the background. So like all of this background that's around, because it's white or it's brighter, it's going to have a value of between 0. It's basically going to be closer to 0. So this is going to be approximately 0, or between, say, 0 and 50. So it's going to have much lower values because it's much brighter. And what we're doing now is, when we have a convolution filter, so what we do next is, if we want to detect, say, the edges of this image, then what you have is you basically have a convolution filter that looks something like this. So you have a convolution filter. So if you want to detect, say, top edges, you go -1, -1, 0, 0, 0, 1, 1, 1. Now, what happens is that this convolution filter, because it's a 3 by 3, will go all over the image. So it's going to go like this, right? Something like that. So it's just going to go in the 2D plane, this convolution filter. And then when this convolution filter gets to this point over here, then you start to get like some values, because over here everything is 0, right? When the convolution filter is here, -1, -1, -1, and 1, 1, 1. If you multiply this with the background pixels, so in a convolution, remember, all that was happening, and this is something we covered last time, is what you do is, if you have an image slice, which could be this image slice, and it will have some values like 0. This would have like values like 0, 1, 2, 3, 4, 5, 6, 7, some values. All that happens is like you multiply these things element by element, right? That's all that's happening in convolution. And then what you see is that when this convolution filter reaches this point, which is just the background, it's going to have a 0 value, correct? But when it reaches this point, when it reaches the top edge, so if it's, say, it reaches this point, what's going to happen is, like, because this filter at the top is -1 and the background values are 0, so this row is going to give me, say, an output of 0. Then this middle row is also give me an output of 0, because the convolution filter is 0 anyway. And then when it reaches the top edge, this row is going to give me some positive value. So the value could be, say, 150. So what's going to happen is, like, every time you take this convolution filter throughout your image, every time you hit a point where it's going from white background to dark values, or basically like smaller pixel values to dark pixel values, that's every time where this thing will give you a positive number. So everywhere else, like everywhere else in the image where this is where there's this yellow highlighter, everywhere else in this image, this convolution filter is going to give me a value of 0, right? So everywhere it's going to give me a value of 0. But at any point where it reaches a point, like, for example, over here, anytime when it reaches this, because the values are -1, and here are 1, 1, 1, at this point, it's going to give me a large positive value. So maybe like 120. So what happens is when this filter goes through this image, because it's going to give me large values at only points which are top edges, or which are points that are transitioning from white background to dark background, then this is exactly where it's going to detect the top edge. So this is how a top edge detector basically, this is how manually these features could be assigned. So when you say you want to do something like, say, basically a vertical edge, the values of the filter could be changed to like -1, -1, -1, 0, 0, 0, 1, 1, 1. And then what's going to happen is when this filter goes through the image, it's just going to find points that go from white regions to dark regions, but in the vertical plane, right? So it's going -1, -1, -1, and 1, 1, 1. So you see it's going from like white regions on the in the background on the left, and then dark regions of the digit on the right. So it's actually found a vertical edge, which is the left vertical edge, basically. So I just want to give that background before I started looking into this, started showing you like how the top detector works, or how this edge detector works. And like these are, in this case, we are manually, like when we're doing this, in this case, we are manually designing the filters. So like this, if the filter value is -1, -1, -1, and then 0, 0, 0 over here, and then 1, 1, 1 on the right, then that's a vertical detector. But in the real case, when you say in the deep learning model, when you define your convolution, or when you say, oh, I need my first layer as a convolution layer with X amount of filters, or X amount of layers, then that's when the model is learning these filters. But we'll get to that very soon, so don't worry about that now. I'll just go in and check if are there any questions on thanks for posting this, Vinayak. I missed Korean's blog post. So Korean's also written about week 10 embeddings and recommender systems. Thanks very much for pointing this out. I'll add that to this comment here. Thanks, Naresh, for pointing this tutorial. So are there any questions about, I'm assuming then there's no questions about like how the convolution kernel is then able to find edges, or like top edge, left edge, vertical edge, or like just things like this. So then if you want to do something like blurring, or basically then you just change the values of this filter, and then it is able to do different things, right? So if I make something like, and I'm just saying this as an example, if I make something like 1 at the bottom, and then maybe like minus 0.2, 0.2, 0.2 around, then what's that going to do? It's just basically going to have a value of the pixel in the center, and then everything around it is going to be a low pixel value, which means it's going to be blurred, right? So if you pass this to the image, then you're basically going to blur the image. So these are just examples that I wanted to show you. So when you go back and you read like this section of the notebook, or this section of the Fastbook, you will see basically everything that I've explained, but just being done in PyTorch. So let me show some code for that. So the top edge, if you have a look, this is how we define a top edge detector: -1 at the top, 0, 0, 0 in the middle, and then 1, 1, 1. And as I've mentioned, it will find points where it is going from white background to dark values. So some points, like basically in this row, like in this row 5, it could find these 3 points. So if you have a convolution filter that has these 3, basically if you have a convolution filter, so if you have a convolution filter, say somewhere here, so that's when it will give you a positive value. So then this is just like showing this thing in PyTorch. It's like, let's grab a subset. So we grab row 4, 5, 6, and 6, 7, 8. And basically these are the values that you have. So row 4, 5, 6 are, and column 6, 7, 8 are these ones. So 0, 0, 0, 1, 4, 2, 1, 5, 5, 2, 4, 6, and then 2, 5, 4. So then you get these values for this. It just grabs like a a small part of the main image, and then you just do your multiplication and you do the sum. So see how it's giving a large positive value every time it hits a top edge? That's exactly the idea. But anywhere else in the image, it will give you a small value. So I guess I will skip over this part because I think it's really not like what I've explained. This is just the exact same explanation in the book. So when you go back and you read this section of the book, you will see how top edges can be detected and basically everything that I've said. So then the next thing I do want to highlight is like mapping a convolution kernel. So what exactly happens is, and this is something I did touch upon briefly in the past many times, but what you have, so what happens is, let's say if I have my input image that looks like this, right? And my kernel that looks like this. So as it says over here, your kernel is going to go from top left and then to the top right and so on. So the kernel, so this kernel is going to start somewhere here, and then it's going to move one row to the right. So it's going to start in the next row, then it's going to move one row to the right, then it's going to start somewhere like this and so on. So this kernel is then traveling or basically covering this whole image. So this is what this thing is doing, is like mapping a convolution kernel. And then in this case, all that FastAI is doing is like it's finding this grid of the coordinates in a list, in a nested list comprehension. So all it is saying is like, okay, let's start with, because this kernel is going to go like all the way, you could find the coordinates at which the center of the kernel lies. Like these could be the coordinates, you could define them manually. Of course, all of this you never have to do in your own. Again, like PyTorch can, this is this part of the book is just showing you things manually and like just showing you like you could do this convolution kernel mapping on your own. You could map the, basically you could do this map the kernel to the image on your own, and all they're doing is like defining these set of grid points. So like you start with top left 1 1, which is this point. So x1 basically, if let's say these are the 1 2 3 4 1 2 3 4, so you start with 1 1 1 2 1 3 1 4, and then so on 2 1 2 2 2 3 2 4, or so on. So basically you just define these grid points, and then these are the grid points at which you do the convolution, and you get some value. So you can show the output image, and as you can see, if I map my top edge detector to my whole image, all it has done is that it has detected the top edges. So see how it is dark at the top edges. It's just detected these, it's done its thing. And you could also have like left vertical detector, so you can see how it's dark every time on your left edges. So these are the points here, and that's pretty much it. And then you'll see, as I've said, like the convolution kernel is basically going over the, or being mapped over the whole image. So in this example, there's this paper, A Guide to Convolution Arithmetic, which is actually a really good paper that I would recommend reading. So if you have time and you want to understand convolutions, and you want to understand like, and you want to just get in the practice of like just reading papers, this is a good resource to get started. So in this case, they just show like various mappings of various strides and various convolutions. And you see that in this case, if my image is represented by this light blue at the back, my convolution kernel, which is 3 by 3, is represented by this dark blue at the top. So what's going to happen is like, let me just paste this in here so I can explain how the output comes. So you have your image at the back. So let's say my image values are say 10, this one is 20. So I'm just, these are not the kernel values, right? The thing at the top, this thing at the top, oh, that's wrong, that's not a good color for this. This thing at the top, like this bit, is my kernel. So this is my kernel that looks something like this. That's my kernel. At the bottom, this whole thing at the bottom, that's the image, right? So the image could have some values, but then what I'm doing is my kernel is multiplied by like this 3 cross 3 map. Every element, let me try this. So every element, like this element, this element, this element, this, and the 9 elements, basically they multiply with each other, and you take the sum. So you multiply whatever the value of the kernel is, and then whatever the value of the image is at this point, Same thing for this point, same thing for this point, same thing for all points on the 3x3 grid, and you take the sum. So this green thing represents your output of applying the convolution to this 3x3 point. Same thing over here. Now you can apply a convolution kernel to the top right, then you apply the convolution kernel to the bottom left, and you apply to the convolution kernel to the bottom right. So see how what happens is, like, you had an input of 4x4. When you applied a 3x3 kernel on top, your output size became smaller. So this is something I want you to remember when we go next and we start looking at padding or all that stuff. What I want you to remember or see from this image is, like, you have some input image, then you have a kernel size of 3x3, and then the output is actually a smaller size feature map than the input itself. So the output is 2x2, whereas the input was 4x4. So that's just the basics of, like, applying convolutions. And then this section is just applying those convolutions in PyTorch. So you can see the good thing about PyTorch is, like, you don't have to apply convolutions one by one. The one thing it can do is, like, convolution. Basically, your PyTorch accepts the convolution kernels in this particular. I will explain exactly what each of these things mean, and your input is in this thing. So what PyTorch can actually do is it can apply multiple convolutions. So, like, it can have these convolution operations on multiple images. So that's why PyTorch is really fast. And the next thing is that PyTorch can do these operations on the GPU. So, like, that's the reason why when we run GPU or when we're using PyTorch, it's really, really fast, because it's doing all of these things parallelly, right? So what that means is, instead of, like, in this example, I've just applied one kernel to one image, what PyTorch can do is you can have multiple or so on, multiple images, and then this kernel is being applied to this position, this position, this position. Basically, all of these three multiple images then are being applied, and all of this operation is then happening parallelly in PyTorch. So in this section, all this part is, like, you just basically define. So it's just showing, like, you can have multiple kernels that can be applied to multiple images. So all they're saying is, let's define some edge kernels. So your left edge, we already know what the left edge looks like. If I say left edge, so you can see this was my left edge kernel, right? My top edge, remember, top edge was -1s at the top and 1s at the bottom, and then you define two more, which is like diagonal edge. So you can see how this one is -1 at the diagonal, and then 1 at the center diagonal. So it's going to actually find diagonals like this that look at a slant 45-degree angle, and then similar for the diagonal edge 2, which is going to find diagonals like that, right? So those are the shapes. So again, diagonal, one is finding diagonals like that, the other one is finding diagonals like that. So all you can do is you can define your edge kernels. You basically stack all of these kernels in your torch, and you can see now my edge kernels are of shape 4x3x3, which means I have 4 kernels of where each kernel has a size of 3x3, correct? So all you can do is you define your data block, which is this is just MNIST. This is something we've done in the past. So you just define your MNIST data block, and you define your data loaders. You get the first batch, which looks like this: 64 by 1 by 28 by 28. What does this mean? This means you have 64 images of single channel where each image is of size 28 by 28. Okay, so the shapes of this have been explained here. Mini batch. So PyTorch, whenever you check shape, PyTorch shows number of channels first, and then it shows the height and width. Okay, same thing for weight. For the filters, you have the channels, in channels, height and width of your kernels. And then for the mini, or basically your batch shape becomes like mini batch, which is the number of items in your batch, the number of channels in your particular image of one item of the batch, and then the height and width of your image. So how do I read this when I'm looking at this? Like, my first batch is of shape 64 by 1 by 28 by 28. I read this like I have 64 images. Each image is one channel, and the each image height and width is 28 by 28. Okay, so all I do, I move them across to the CPU. So let me run these parts. All I do is I move them across to the CPU. One thing you will see is like the weight filter accepts like my kernel to be like a 4D input. So for now, because we're doing things manually, all we have to do is we have to add that dimensions ourselves. So remember like our basic our kernels were like 4 by 3 by 3. So all we have to do is like we add this dimension 1, which just signifies that our input image has one channel. Okay, so all we do is over here. So how do I read this? It means I have I have 4 kernels. Each kernel is of shape 3 by 3. So these kernels are like top edge. So this is one of those kernels. So you have 4 of these kernels, which are 3 by 3. And then this 1 is just represents that my input has one channel. Okay. So all I do that. And then now I'm ready to apply the convolution operation. Okay, so I take my batch. So this is when I was saying like PyTorch can apply multiple kernels to multiple images, and like all of this happens parallelly, and it's not something we have to worry about how that works. So we just say, oh, PyTorch, please use the conv2d operation. So f.conv2d accepts 2 things. It accepts your input, which is your input image or your input feature map, and it also accepts your kernel weights. So in this case, my edge kernels are this. So remember, this is what my edge kernels are. This one is the vertical left detector. This one is the top edge detector. This one is the diagonal detector. And this one is the second diagonal detector. So what PyTorch is going to do, it's going to apply these 4 kernels to all images in my batch. And then you get an output of 64 by 4 by 26 by 26. So it's really important to see what just happened. So remember, my input shape was xb.shape, and my output shape is now this batch features.shape. Can you see the difference? So when before applying the convolution operation, we had 64 images of 28 by 28, and we had 1 channel images. Now we have 64 images of 26 by 26, and we have 4 channel images. So I guess at this point, it's really important to in your head to understand what exactly happened. And something when I was doing the Fast AI course, something Jeremy kept on saying and really stressed on was that it's really important to see the input shapes, and it's really important to see the output shapes, and try and map the two. So try and map like what exactly happened. So let's see what exactly happened, or like why do we have 4 channels as outputs, and why is like this 26 by 26, right? I'll just go check if there's any questions. Actually, I would appreciate do one thing. I'm just going to take a minute. I think this will be a really helpful exercise. Let's make this very much more interactive. So take a minute to think like, I've already given you all the details. I've already explained everything that's happening in the convolutions. But take a minute to first, let's brainstorm, why was my input 28 by 28? And when I applied a 3 by 3 kernel to this 28 by 28 input image, my output is 26 by 26. So why do you think that happened? So I guess just post over here and see like if you have an example. So come have a post, and I'm just gonna, let's just make this more interactive. I think this is the best way forward. So while you're posting your answers, I also want you to think, why do you think our input image had 1 channel, whereas our output feature map has 4 channels? So what changed? So these are the 2 things. And meanwhile, I'll start drawing some, I'll start posting the answer here. Okay, Vinayak saying if we have an RGB image, we don't have an RGB image. That is incorrect. I think Vinayak, you're jumping ahead. We don't have an RGB image. On this tensor tot size 64 1 by 28 by 28, if we apply 4 filters, it will produce 4 tot size 64 by 1 by 26 for each filter will be stacked and make a torch size. This size is reduced from 28 to 26 because of applying the filter. That's perfect. But let's just quickly wait for Kevin and Vinayak to finish. I really want to see what they're looking at as well. So Kevin says, I believe the reason is because our kernels are 3 by 3 size. So when we compute each location, we lose 2 pixels in each direction because it won't be able to stride past the 28. That's correct. I'm showing it on 9 wide. So if you have 1, 2, 3, 1, 2, yeah, that's correct. That's a really good explanation. So that's why we lose the 2 pixels. That's correct. I'm so happy to see each one of you got it. So I guess then what I'm explaining, this is I guess also a good feedback loop that what I'm explaining is making sense. So I will just still try and summarize. I know all of you have got it, but remember in our input batch we had 64 images, right? And each image looks something like this. So you have 28 by 28, and then your 64th image is also 28 by 28. So you have 28, so on. So I'm not gonna draw the whole 28 lines, but that's just how the image looks like. And then what happens is you're telling PyTorch that I have 4 kernels, so 1, 2, 3, and 4, and they're all single channel. So all you're saying is, let's take the example of one image, right? What's going to happen is like when you apply this one kernel to this image, your output is going to be of shape 26 by 26. Why? Well, this is just exactly as I explained over here. So when the kernel of 3 by 3 was being applied, it first got applied here, then in this position, then in this position, and then finally here. So when you had your output of 4 by 4, your output is 2 by 2. So you're losing 2 basically, because you can't really have you can't really draw, like it can't really go out of bounds. So that's why there's only like 2 by 2, or there's only like 4 positions where this kernel can be applied. The 4 positions are this one, this one, this one, and this one. Those are the 4 dots where this kernel can be applied. So that's why your output is 2 by 2. Similarly, when your input is 28 by 28, there's only 26 positions, like this one, so on over here, and then like this. So you only have 26 positions where this kernel can be applied. So that's why your output is 26 by 26. So we solved the first idea of like why the output is of shape 26 by 26. So now the next thing is, even though my input had like one channel, so even though my input had one channel, then why does the output have like 4 by 26 by 26, right? That's because 4 of these kernels get applied. So this one as well. So what you have is you don't have one output of 26 by 26 per image, but you actually have 4 outputs of 26 by 26. So when you stack them together, your output is going to look like 4 by 26 by 26. I hope that makes sense. So that's why when we're going here, that's why for each of the 64 images, when you had an input of like 28 by 28, you get for each of those, you get an output of 4 by 26 by 26. So this is really exactly what's going on when you apply convolution. Now, in deep learning, or when you say you define your ResNet, so if you go from torch vision.models import ResNet, let's just say 18. When you define a model like this, which is a ResNet 18, or like a much bigger models, which has convolution 2D operation right at the beginning, and it's like saying stride and padding, don't worry about that for now. It has a different kernel size, but it's saying let's try and understand what this says, right? So the convolution, this operation is saying each of my input images, don't worry about anything else, okay? So we're just looking at the conv1 operation of a ResNet. So what this is saying, my input images have 3 channels. I haven't shown you how that looks like, but let's just say, follow me along as I'm saying this. My input images have 3 channels. I want my kernel size to be 7 by 7. So in this, sorry, not over here. In this example, we have 3 by 3, but all this is saying is like, I want my kernel size to be 7 by 7. And I want 64 such kernels for each image. Make sense? So then for each image, you're going to get 64 outputs. That's why your output, when you do something like this, your output is going to have 64 channels. I hope that helps. Another way to do this would be my input has shape that. Let's just create a conv 2D operation. I say my input channels is 1, my output channels is 128, and my kernel size is say 3 by 3. So I'm just creating some conv, and then I could do conv xb, and I could say shape. That should work. Cool. So now you can see, like, now you can play around with this. All I'm saying is, hey, PyTorch, please apply this convolution operation. My inputs have 1 channel because they're all 1 by 28 by 28, right? So if I just check the shape of one element of my batch, it has 1 by 28 by 28. My inputs have 1 channel, and I want my kernel size to be 3 by 3, which is this exact thing. And all I'm saying is, instead of like having 4 kernels that we define, like edge detector, all of these edge detectors, PyTorch, please define 128 such kernels for me, and you do the learning. So I don't know how you define these, like what the values of these kernels are. You do the learning, and this is how a ResNet will learn how to apply convolution to the image. So I just want to, I guess, I kind of explained a lot more than and spent a lot more time in this section than actually in the book, but I think it would be helpful. So that's where I'll stop. So now when you apply the convolution operate, coming back, because we were looking at the edge kernels, if you just plot the output of like the top edge or the left edge detector, you can see like your image looks something like this. I had a misunderstanding for the longest time that the number of filters had something to do with the sizes, but the size is actually determined by the kernel size and not the number of filters you use. That is absolutely correct. Yes, the number of filters, all it defines is the number of output channels. So if you have 128 filters, which I had in the example before, you have 128 output channels, because each kernel is then basically have 128 kernels that are going to be applied to the input image. Vinayak, let's not jump to the RGB. So this is something we're going to cover just over here. We're going to cover the RGB image. I don't remember the exact section, but we're going to cover RGB. So I'm not even going to look at that question. Okay, give me 1 sec. So now we're next to strides and padding. Oh, so now we're next to strides and padding. So what does it mean? So remember when I just created, like I showed you ResNet 18. And I showed you like the conv1 operation of this model looks like it has something called stride and padding in it. So what does that mean? What does this stride, what does it mean to say, hey, convolution, please have a stride of 2 by 2 and please have a padding of 3 by 3. So what does that really mean? Let's have a look. So then one thing then is happening over here is my input is say 1, 2, 3, 4, 1, 2, 3, and 4. So let's say my input is 4 by 4, right? And we were going to apply a kernel of 3 by 3. So if we apply a kernel of 3 by 3, we could only apply it to position like that one, because then that's where the kernel kind of be applied. We could apply it to this position, we could apply it to this position, and we could apply it to this position. So what's going to happen is like you get the output, which is 2 by 2, correct? Now, every time this happens, or every time because deep learning model would have like multiple convolution operations. So if your input is say something like 28 by 28, if you're passing that down to a 50-layer network and you keep losing 2 dimensions, or like basically your spatial dimensions are lost by 2, so your becomes 26 by 26 or so on, there's going to be a point where you're going to be 1 by 1, and then you can't apply a convolution kernel anymore, right? Because then you just have 1 point. So how are you going to apply a convolution, a 3 by 3 convolution to a 1 by 1 point? So the idea is then there's something called padding. So what is padding? It just means you just introduce another layer of zeros around it. Okay, so this is how that looks like. So now instead of your image being 4 by 4, it becomes 5 by 5. So these are all, there's like different ways of padding. I'm just showing you zero padding right now. So these are all zeros, right? Sorry, not these ones, just the gray ones outside. So 0, and they should be like that. So the outsides are all zeros, right? And now what's going to happen is like you get these extra positions where the convolution kernel could also be applied, correct? Because now at this position, you still have these options, even though like this part of the image is all just zeros and the actual information, image information is only in my highlighted yellow part, and the highlighted gray part is all zeros. That's completely okay, because it's only happening in this section. Like, sure, you're mixing the image information with zeros, but at least what you're going to have is like you're going to have an output of shape 4 by 4, instead of like the same. You're going to have the output size which is the same as the input size. So that is what padding 1 can do. But if you have like a padding 2, so you have, say you introduce another padding and you have more zeros, then your output could be 5 by 5, even though your input is 4 by 4. So this is what is called padding. And one of the best places to learn more about padding is just search the FastAI docs, FastAI padding. I just want to see, I think there was like this idea of reflective padding and everything in the FastAI docs. So I just want to see, oh, there it is. So see how, just have a look at this part of, or this part of the image. What you can do, there's like, instead of just adding, and I'm not just showing you what padding is, which is what's mentioned in the book. I'm also trying to explain like there's different types of padding. So instead of like just, what you could do is, instead of just like having these zeros, you could have like this element at these 3 places, then this point at these 3 places, and so on. So then that kind of padding is called border padding. So you could have this one here, this one here. So it's like that kind of padding is called border padding. In reflection padding, all you do is like you start reflecting this section. So this one comes at these 3 places, then this point is reflected to come at this point, and so on. So this is just reflection So you can see like how the images look differently when you pad them differently. In most practical situations, reflection padding is the way to go, and it kind of works a lot better. So I'm just sharing that experience with you guys. So that is padding. Okay, so that's the idea of padding. The next thing is, what is stride? So let me draw 1, 2, 3, 4. 1, 2, 3, 4. So now you apply a convolution here, right? This is my first position. Then the second position that you would have applied the convolution, 3 by 3 convolution. So let's say I have my input of 5 by 5. I apply my convolution at this first position. Then ideally what you do is you go from this to your right, so you apply the convolution at, so see this was point 1, 1, which is where the convolution is applied. Then you would apply the convolution kernel at point 1, 2. But if you define and say a stride of 2, then you don't apply it at 1, 2. Rather, you apply it at 1, 3, which is this point. Okay, so then your next convolution kernel gets applied at this point. And then instead of applying at 2, 1, you don't apply the convolution kernel here. You apply it at this point 3, 1, and similarly 3, 3. So the 4 points where you apply the convolution kernel then becomes 1, 1, 1, 3, 3, 1, 3, 3. That is what it means to have a padding, or sorry, a stride of 2 by 2, which means like you're taking bigger strides. So you know, when we're walking, we just walk like one, let's say that's the normal stride. But when you start to take bigger strides, that means you're taking bigger steps. So our convolution kernel is now taking bigger steps, it's taking bigger strides. So this is this idea of like having strides and padding. So while padding on one end makes sure like it adds extra dimensions, and it makes sure like our input is this the output is the same size as the input. Strides on the other hand make sure like if you have, let's say you have an input image size of let's say you have a massive image 2160 by 2160. It's going to take ages to keep applying convolutions to this and bring it down to say like 64 by 64, things like that. So what you do is like when you have a really big input image, you have a padding, you add a stride of like stride 2 and all that stuff. So I just want to explain what padding and stride are. Wow, I took a lot of time explaining this few sections. Anyway, let me just go and have a look if there's questions, which there are, which is really good to see. Can kernels or filters be more than 4 in number? Yes, that is correct. They can be. Vinayak, I'm not going to read this because I'm going to come back to RGB. I'm going to come back to RGB in a sec. Maybe a bit more could be something like this. Oh yeah, thanks Anush for pointing this out, that this is really helpful. Like you have in channels that I'm just generally I was being lazy, so I guess thanks for writing it like this. Can anyone tell me, is there any forums for solving collab notebook errors? Fast AI forums, or even just post them here. So if you try forums.fast.ai, and then if you search the kind of error that you have, or like say collab error, I don't know, if you search some things, you'll see like there's all these errors that are being discussed, or you could do them here. When would be a scenario when you would want to increase the stride just to reduce the image size faster? Yes, that is correct. So see ResNet. I keep going back to the ResNet example. So ResNet 18.conf1, right? That was my first. So in this case, you have a stride 2. So you have a bigger stride, but you also have a padding 3 by 3. Let's see ResNet 34. Is that the same case over there? And what about, but the kernel size is 7 by 7, so that makes sense. So when you have a basically I keep referring the ResNet, which is going to be next, but it's just the architecture that has a bunch of convolutions. And mostly what I've seen from reading all of these different papers is that you have bigger strides in the earlier layers and you have smaller strides in the later layers. So you have bigger strides in the earlier layers is because when your input image size is massive, you just stride and you have like big strides. So you keep having all of these like massive strides. So you cover more ground in your earlier layers because it's going to take a lot of time if you go at an input image size of 2160 or like 1600 by 1600. I'm just bringing up examples, but you have very large image size, and that's when generally you'll see like the earlier layers have a bigger stride. You can post over here. Oh, thanks, Gurjesh, for pointing that out. I guess it would kind of be stride versus, sorry, oh, you cut it off. Okay, I'm just gonna skip then. I'm gonna keep moving on. All right. This part is really important, and I quite like, and I was quite amazed by it as well. So I guess let me explain it to you. It should be self-explanatory, but let me try. So let's say you have an input image of capital A, B, C, D, E, F, blah, blah, blah. And you have your kernel represented by alpha, beta, gamma, and delta, right? So all this is saying is my input image, instead of like, just having symbols to represent pixel values. Okay, so this is just like variables, and my kernels are like this: alpha, beta, gamma, delta, right? What's going to happen when we apply this convolution kernel? So you first apply this at this position, then over here, then like this, and then at that position, right? So top left, top right, bottom left, bottom right. So this is how it looks like. When you apply this to top left, this gets applied here, and the output that it yields is, say, maybe capital P. When you apply this kernel to the top right, the output that maybe it yields is capital Q. When you apply this to the bottom left, the output that yields is maybe R. And same thing at the bottom right, the output that yields is S. Now, instead of just looking at this from like this operation as a special convolution operation, we could also look at this as a standard machine learning, as a standard matrix multiplication operation. So let's see how that looks like. Oh, sorry. Then basically, this is just like saying, oh, P is equal to alpha times A plus beta times B plus gamma times D plus delta times E, right? Q is alpha times B, beta times C, gamma times E, and delta times F, and so on, right? That's okay. So P is this value, Q is this value. All you can do is like, you can represent these equations basically in the, like P is equal to this, Q is equal to this, as a form of matrix multiplication, like this. So if you have your input image flattened as A, B, C, D, E, F, and so on, and you apply your first rule, because remember, what was P like? P was alpha A, beta B, gamma D, and delta E, right? So alpha A, beta B, gamma D, delta E. So what you can do is like at those positions, you can have those values, everywhere else it can be 0. Same for Q, you could have it like this, same for R, same for Z, same for S. So this gives you your PQRS. All this is saying, or like all this section of the book is saying, is like, it is convolutions are just, this is just like, you can just look at convolutions as matrix multiplication, where there's like these bunch of zeros everywhere else. So the zeros actually are the untrainable things. Like these aren't the things that you learn. So when I was saying like, you actually just learn these values, alpha, beta, gamma, and delta. So remember, until now, all we've looked at is kernels that we define with values -1, 1, and so on. In actual deep learning, when you training your, when I keep saying actual deep learning, all I mean to say is like practical, when you implementation. When I say actual things, I just mean like the implementation of it. So when you're implementing things in PyTorch, all it is doing is like, you can look at this, it's just going to train these, it's just going to train the model to learn these 4 values, alpha, beta, gamma, delta. And then you can just look at that in terms of like a matrix multiplication operation where everywhere else is 0, which is untrainable. So that's the point of this. That's just like a good point to see, is just like a different viewpoint of looking at things. Okay, before we move on to the first convolutional network, so actually I'm going to go today we're going to wrap up 1.2 and we're going to go all about 1.3. So we're going to cover until color images from 1.4. So we'll be left with 1.4 for next section, and that's going to be fine. So we're going to cover 1.4 next week, and then straight after that we're going to go into ResNets. So today then I'm just going to cover to 1.3. So let me see, because I want to cover things into more detail. So let me see if there's any questions. Oh, figured it out. Kernel size doesn't really reduce image size nearly as much as stride does, only around the edges, and kernel size would require memory intensive process as well. Yes, that is correct. I'm so glad you're summarizing things better than I am, Kevin. So that's really helpful to see. As Aman just said, I think of it as covering more of the image in a larger stride. Thank you for agreeing with me. One of the formulae I could recollect, the output size. Oh yes, that is correct. There's like there's this Stanford CS231N. So I guess that's what you're referring to. So there's this introduction to convolutions, I guess. Sorry, let me just do a quick Google. Introduction to convolutions CS231N. I guess it's this one. So this is another course run by Stanford and Andrew Ng, and over here there's like everything that I've explained to you so far. You can like have formulas of like, oh, if the padding is going to be 2, if the stride is going to be 3, then what's the output size going to be, and all of that. I never look at the formulas, but some people like to, so it could be very helpful. I'm not saying like one approach is better than the other, but I think this is the place. So I just want to also show everybody who's doing Fastbook, like there's these other resources as well that are really, really nice. So let me just post it in the discussion thread. All right, I guess it's that one. Cool. So now let's just go and create our first CNN. Somebody was typing. I'm just interested in if that's a question. Anyway, okay, I'll move on. So remember, all of this we're doing, we've just understood how kernels get applied, what the shape of the kernels are, how does the shape of the input change when the shape of, depending on the stride and the padding and the kernel size. But the main idea of like, this is all helpful to know, but actually what we want to do is we want to create a CNN and we want to learn the convolutional neural network, right, to do some tasks. So we're coming back to that problem in this section. Remember, our task that we were trying to do was basically trying to classify input images, and the input images were DLs. Is what, did we have DLs defined? Yeah, we did. And the input images were these. You had 3s and 7s. So all we're trying to do right now is going to classify 3s from 7s. So remember from MNIST chapter, we defined like a simple neural net like this. In this case, let's replace that and let's define a simple neural net using convolution operations. So the first operation is a convolution operation that takes one channel inputs. So now you know how to read this. Excuse me. So it takes one channel inputs. You have 30 kernels, or basically 30 kernels for each of those, you have 30 kernels for each image. Your kernel size is 3 by 3, and your padding is 1. So what does that look like? Your input image, your input image is single channel, and I think it's 28 by 28, so we know that from the input. And you have 30 kernels. So these are 30 of them, 30 kernels of size 3 by 3. Padding around this is 1 and stride is 1. So that's fine. So padding around this is 1, right? So the output is also going to be 28 by 28, but 30 by 28 by 28, right? So let me explain what I'm trying to say. So if you just take this, conv equals this. So my input shape is 64 by 1 by 28 by 28, which is just representing this one image. So if I go conv xp dot shape, as you can see, now my output is 64 by 30 by 28 by 28. But then see what this CNN does. It first goes from 1 channel to 30 channels, and then it's going back from 30 channels to 1 channel. So how would you read this convolution operation? You would say, okay, remember now my output. So the output from this is the output from the first convolution operation channel looks something like this, right? So you have still 28 by 28, but you have 30 such channels now. So this is the output. And then to this, we apply the second convolution operation, which says for the second convolution operation, we have a kernel size of input channels 30. So remember, this is my first conv. This is my second conv. This is my out from the first conv. This is the out 1. Okay. So then the second convolution is saying, hey, PyTorch, please apply a convolution of 30 input channels and then have just one such filter. So what's that going to do? When you apply this to this, you're going to get a single output, right? Because it's going to apply these 30 channels, and then it's going to apply, sorry, the kernel size is 3. So you get output of, you just get the output of like this, 28 by 28. So for each position, when this gets applied, because this is 3 by 3, so you have like being applied 3 by 3, then to this point, 3 by 3, so on, so on, so on, you get the output of 28 by 28. Correct? That's what these things look like. Oh, look at that. And exactly, that's it. I swear when I was going through this notebook, I didn't think of the output shapes in such detail, and I never thought that I would explain this chapter by like drawing these things or like looking at the input shapes and output shapes. But now that this whole operation of like this broken CNN can now be represented by this image, and I hope it makes sense as to why the output is 64 by 1 by 28 by 28. So okay, so I hope that this makes sense, that the output is 64 by 1 by 28 by 28. In case it's unclear, let me know. So let's leave it at that. So what you can do is, this is just refactoring, like you can just define a conv operation that takes in some number of input filters and says number of output filters. So you don't have to like define convolution like this. You could just say conv, you could say something like conv number of input filters is 30, output filters is 30. So that would define this. Sorry, this is doing forward, don't worry about it. But all I'm trying to say is like, all this is doing is just creating like this, is first it's creating a convolution, and then it's just returning my result. So sorry, actually what it is doing is like, it's creating my convolution, adding value on top. Fair enough. So then why did it say, what if I go 1 by 3? Oh yeah, that's fine. I hadn't defined it properly. So I could just, this is just the convenience of like, instead of writing conv2d and value, you could define these two things in this function. So if I say my input channel is 1, output channel is 30, it just defines this sequential. So this is just the PyTorch convenience. So now I could define my simple CNN. Sequential just means like you apply operations 1 by 1 by 1. So this conv is just going from like single input channel to 4, because you have 4 kernels that get applied. Then it's going from 4 to 8, it's going from 8 to 16, and so on. And remember, in each of these places, you have a padding of 1. So that's completely fine. So then you start, and this just shows like what the output shapes are going to be. I'm not going to go into like the details of why the output shape is 14 by 14. I leave this as an exercise. So please come back. This is something you should do. Is like, oh, can you please explain how we go from 30 filters? I will do, Kevin. Just give me a 1 sec, and I will go back to that. But one thing I do want to say is like, as exercise, please come back to this forum and do something like this. For each of these operations, now I've told you how to like look at the output shapes and the input shapes. Please, for each of these things, draw a drawing like this, or like even on a piece of paper, and then look why the output size is 14 by 14, or look at it why the output size is 7 by 7 or 4 by 4, and so on. Okay. So we can define, Kevin, I'm going to come back to that just in a sec. Let me just wrap this up. So I define my simple CNN like this, which is just like the sequential of convolution operations followed by a value. So when I apply that to my input, I get this output 64 by 2, because remember the output is saying output channels of 2 by 2. Finally, we can use this simple CNN in our learner. So this is just like the first lecture. You just have your learner, you have your data loader, you pass this in, and you say, show me the learn.summary. So this is what my model looks like. And then you can say fit. And you see the accuracy is 0.99. So all we've done in this part is we've actually just created a convolution neural network from scratch. So what is a convolution neural network? It's just a network or a neural network that has convolution followed by some non-linearity. So see, in this case, we could classify, this is a big moment. Like, I think I want to highlight how big of a moment this is. For everybody, each one of us, when we started our Fastbook journeys from the scratch, we just use things like ResNet, or we use things that were part of the learner. We never built a model architecture from scratch. So in this case, what we've done, even though it's a very simple CNN, right? It's baby steps. But what we have done is we created our very first convolution neural network to do classification, and it can classify threes from handwritten digit 3s from 7s with the 99.11 accuracy. So I say well done to everybody who's followed me till here. So I think that's a really good step, and this is something to be proud of when we finish our chapter today. So now I'm going to go back to this point of like, can you explain how we go from 30 filters to 1 filter? So so we're going back up. So remember, we created like this small CNN, which looked like this, and I passed in my input. So the first convolution operation had 30 kernels of 1 channel. So you have your input looks like this, 1 by 28 by 28, right? This is my input. And you have 30 kernels. So you have 30 kernels of 3 by 3 size. What we're doing is we're applying these 30 kernels, so your output becomes 30 by 28 by 28 because you had a padding of 1, correct? So this is what my output looks like, 28 by 28, but 30 such things. So each of these, so it becomes like a 30 channel block, right? Now, my kernel in this second part was, it said the number of input channels is 30. I want 1 such kernel. So even though PyTorch calls this like out channels, I kind of look at it as the number of kernels. And the kernel size is 3. So this is, let me make this smaller. So it's like this. Right? You have 30 channels, 3 by 3, correct? And then this kernel will get applied to the similar like a convolution operation here. So when this is being applied, it will start at a position over here, like this, then it will move on to this, then so on like this. But remember, now instead of like my input being 1 channel, this is 30 channels. So the first time this kernel gets applied, let's say it's at the top left position, it's going to look like this, right? So it's going to get applied to the input image of 30 channels, and then this is 30 by 3 by 3 as well. So when you apply this whole thing, just don't worry about the depth. When you apply this whole thing, you're going to get output, which is 1 number. Does that make sense, Kevin? You're going to get an output of 1 number because your kernel has 30 channels. It's applying and doing the sum of like all those 30 channels all at once. So you get 1 number output. And because this kernel gets applied at like all these 28 by 28 positions, your output is a single channel 28 by 28. Could you? Oh, how do we determine if it's a 3 or 7? Oh, in this case, this was like a broken CNN. We're not using this for training for 3s and 7s. What we're using for training is this simple CNN, right? So this was just a small CNN that we created. I just want to, this was just to like show like what exactly is going on, and just to show input shapes and output shapes if you apply this to your input. But this is not the model that we use for, learning. For the exact same reason, like the output is one filters, like how are we classifying the 3s and 7s? We are not. So we use this simple CNN that has an output of 2. Okay, so then these becomes your probabilities. So just saying we're using simple CNN. All right, I think I will stop here, even though I wanted to finish to 1.3. I will stop here. And when you go back, I think this week, because it's already time, when you go back this week, then do the following, and you'll really feel like you've learned a lot from the exercise that I'm about to tell you. So do this. When you go back, just have a look at this simple CNN. Like I'm drawing these images to explain, like when I had an input of 28 by 28, then why does the output have 1 filter and so on. Like I draw the output of using this broken CNN. You do the same thing for this simple CNN. So go back and figure out why the output is 64 by 2. Okay, I want you to, I want somebody to post in the forums and just say like why the output is 64 by 2. Okay, and we will get back to the RGB. I'm so sorry, Vinayak. I kept saying we're also. Oh, that's correct. Yes, you got it though. I won't explain it now, but you've got it. That's a good understanding. So I'm sorry, Vinayak. I kept saying we're going to look at RGB later, but we're out of time, and we're going to look at RGB next week. So thanks everybody for joining me, and I will see you guys next week. If you have any questions, actually, please post them here, and I will answer them. But thanks for now, and I'll see you guys next week.